Uh, Thank you very much, Sahir, for agreeing to be here this afternoon. And thank you all for joining us. I'm really pleased to introduce to all of you Dr. Sahir Bhatnagar. He's an assistant professor in the Department of Epidemiology and Biostatistics at McGill. And he joined this position in 2018, just a little bit before the pandemic, which is why perhaps we haven't invited him so far to speak at CORE. His work focuses on developing statistical methods for analyzing high-dimensional data in genomics and radiomics. And he also has a position in the Department of Diagnostic Radiology. I would just actually like to share with you Sahir's excellent website where you can learn a lot about what he does. And in particular, I'd like to draw attention to his teaching work. Sahir has put the notes for EPB 607, which is a popular course, introductory statistics course, in book-down format on his website, which makes it really easy to read, and it's really nicely done. So I encourage you to take a look at this and his other books. And he has also written a lot of R packages, which here you can see on his code, and you can see that they've been downloaded an impressive number of times from CRAN. This one's been downloaded 86,000 times, this one package alone. So a very nice and informative website. And I'm very glad that he's here today to talk to us about, I think, a topic that interests many of us, about the relevance of machine learning. So Sahir, it's yours. Thank you.
Thank you so much, Nandini, for that very kind introduction and highlighting the website, which I encourage all my trainees to go through that process. Whether you stay in academics or not, it's always nice to have some sort of online presence these days. You never know who's looking for potential employees. So thank you again for highlighting that. So yeah, today I'll touch a little bit on kind of this idea of prediction versus explaining, and a little bit on machine learning, but really from a statistics point of view. I have my own experience, and I think one thing I've learned over the past couple of years is really, it depends on your training, the people you meet, which really influences your view on such a debated or contested topic like statistics and machine learning and AI, and particularly when it comes to the health sciences. I think that's where really there seems to be a lot of debate about the utility of these tools and how they're being used, how they're being implemented. So again, a very one point of view, really it's meant to be descriptive. I'm not trying to kind of pick a side or say one is better than the other. It's more just, in my experience, what I've seen and what I'm trying to highlight. And so, yeah, as was mentioned before, by Susan, feel free to raise your hand or send something in the chat if there's something that's not clear during the talk. So, yeah, what I wanted to start with actually is just, sorry, you don't see my screen yet, I guess. Right. So what I want to start with is like just a quick Google search of kind of what happens if I type in something like a risk calculator. Okay, and so there's a lot of links, but I'm kind of just interested in kind of the first thing that comes up. So I'll click on this first link here, and we end up with this risk calculator called the absolute CVD risk benefit calculator. Okay, and so if you're not familiar with this, there's a little bit going on here. So I just wanted to explain a little bit what's happening. So the way this calculator has been built, and if there's any physicians in the room, I'm sure you're very familiar with this idea. But essentially, what this calculator is doing is calculating some sort of 10-year risk of experiencing a CVD related event, so cardiovascular disease related event. Okay, and in this specific risk calculator, there's actually 4 options you can choose from. So if you look, if I switch to the Q risk, you'll see that the inputs actually change. And so really depending on what data was used to develop these calculators, you'll see that there are different inputs to this risk calculator. Okay, so I'll just focus on the first one that I see, the Framingham score. And so this is really for, as it mentions here, you know, heart attacks, angina, coronary, heart failure, and so on and so forth. Okay, and so what the calculator is asking you to do is you know, fill in this information. So I'm assuming you know you're in the clinic and you're at risk for CVD, and so you have to input all these features or characteristics or predictors or covariates that we call in statistical literature. Okay, and so what happens is, you know, I can change this maybe to male, and you see right away that, you know, the number of red faces compared to the blue faces change. Okay, and so that's just the proportion of how many would experience the event out of 100. Okay, so if, you know, going from female to male, I can see already I go from a 98, sorry, a 2% to a 4% risk. Okay, and then, you know, I can increase the age, and you'll see again there's an increase in the in your 10-year risk of experiencing a CVD related event. Okay, and so, you know, you can kind of keep going down the list, and you see that there's, you know, several different inputs here, and each one, you know, kind of changes the risk in a different way. Okay, but you're not exactly told, especially, you know, just looking at this specific calculator, what is affecting, or how, in what way, like what's the actual numerical relationship between the two, between the inputs and then the actual risk that you get. Okay, and of course, you know, we can get a little bit more into the details. You can actually take a look at the FAQ here, which is really well done, I think. And you'll see that they provide, you know, a lot of information about how to use this calculator, and they also provide the original publications, I think, as well, somewhere down here. Okay, but you know, kind of the main message, the main takeaway I'm trying to explain here is just that, you know, we have a whole bunch of inputs, and we get this 10-year risk. Okay, and so based on that, my you know, maybe my first question to you is I have this graph here. Okay, so this graph is you know, a very simple one. On the x-axis, I have kind of explanatory power, and on the y-axis, I have predictive power. Okay, and so if I were to, you know, you don't have to answer me right now. Maybe, you know, your opinion will change throughout the talk. But I want to ask you this question, and I want you to think about it a little bit throughout the talk. Is, you know, I've kind of split this graph into 4 quadrants, and if you were to try to place this CVD risk calculator that I just showed you in one of these 4 quadrants, you know, like where do you think it should land? Like, do you think, so for instance, should it land in quadrant 4? In other words, like, this is really a tool to explain what's happening, explaining how these factors are associated with that prediction. Or is it the opposite? Is it somewhere, you know, in quadrant 1, where really I don't really care about that relationship. All I care about is the predictive power and the prediction. Just, you know, I'm going to give you the inputs and give me the output, and that's all I really care about. I want to, obviously I care that this has been validated. This is an important tool. But you know, between these 2 axes, I want you to try to think a little bit more about where this this tool would land. Okay, and so I'm going to go through my talk, and then I'll ask the same question at the end, and kind of see what, you know, what you think, and maybe you can let me know if you've changed your mind from the original question. So as mentioned in my abstract, I mentioned this paper, this very famous paper by Leo Breiman, and so I say famous is a relative term for statisticians. It's a very famous paper, and so in this kind of setting, the setting of today's talk, really what I'm focusing on are these explanatory variables, or these predictor variables, like you saw in that input, so like age and your cholesterol, and your BMI, things like that. So that's what I would call the X's in this diagram. And they all have arrows pointing towards a single response variable. Okay, and the response variable can be different things. It can be kind of time to CVD. It could be, whether or not you experience a CVD related event. It could be many things, but specifically for this talk, I'm kind of assuming there's one response variable of interest and then, several predictors of interest. Okay, and we're really trying to figure out, what is the relationship between these two sets of variables. So this is very a classic way of thinking in statistics. It's what, as I mentioned in my abstract, dominated 20th century statistics, where we really focused on, regression and understanding the relationship between these two sets of variables. And so what Breiman, one of the first things he mentioned in his paper is that, the way this relationship happens, we should try to see it through this sort of box here. Okay, so this box here is shown by nature. And so we have X, which are the inputs. It goes into this box. Nature, functions on these inputs and then eventually spits out some sort of response variable. Okay, and the contrast that he's really portraying in his paper are the different ways of filling in this box. In other words, how do we actually figure out or try to interpret or try to deduce what nature is actually doing? And that's really the crux of what we try to do in statistical analysis and more general in observational research. We're trying to figure out what the processes are that go from the inputs to the outputs. So there's basically two schools of thought or two ways you can think about analyzing the data. And I myself, when I'm consulting on a statistical problem, I try to ask this question is, are you interested in prediction? And so what do I mean by prediction? So I need to define that a little bit. And so prediction is really focused on, what the Y variable will be in future input variables. So in the CVD risk calculator example, I'm inputting the variables of a patient that presents in front of me. And now I want to predict their 10-year risk. Okay. And so it's, one thing, in popular culture that comes to mind is the famous, kind of Netflix prize or Netflix recommendation systems, right? So there's kind of a lot going on behind the scenes and there's a lot of different inputs, most of which we don't even see ourselves when we're on the application. But in the end, what you do see when you see a list of recommended titles, right, on the homepage, those are in fact predictions, right? And so you don't know how it got to that point. All you know is that these are the responses. So these are what you're being recommended, and this is all based on some sort of machine learning algorithm, if we can, for lack of a better term. Okay, but that's really when we think about prediction, this is kind of what I think about. And then the second way to analyze data is when you're interested in explanation, right? So when you're trying to extract some information about how nature is associating the response variables to the input variables. Okay, and this is a little bit maybe cynical of me to think about it this way, but really the way I see it, unfortunately, is what some people have referred to as stargazing. Okay, so what do I mean by stargazing? Okay, so this is an R output, and I'm not sure if the other softwares do this like Stata and SAS, but R, for whatever reason, developed by statisticians, prints these stars here, right? So all these stars. And so what that's kind of emphasizing or what's brought the culture and kind of some of the debates statisticians have in terms of p-values and confidence intervals is that people run these models and then look for the stars. So the stars basically mean that there's some sort of statistically significant association, whatever that means. Is basically trying to say that, hey, this predictor in my model is very important in or is very associated to my response variable Y. Okay, and whether we say it or not, we always hear the mantra that association is not causation. But whatever we say on the surface or whatever we say to get past the journal editors, we all see this as a causal model. I mean, most of us, if we're really being honest, why would we care about association? What we really want to know is what are the causal variables? What's causing my response? Why? Okay, and so again, whether or not we're upfront about it, whether or not we state our assumptions that go into these causal analyses, that's what we're actually after. And so this is a completely different way of analyzing data, and kind of the purpose is different, but often what I've seen is that the two things are conflated. So we often use these stargazed models full of stars to do some sort of prediction for a future event. Okay, and so that's kind of the if you can take one thing already away from this talk, is really contrasting those two kind of cultures, and what has dominated statistics in the past century basically has been more this stargazing approach, unfortunately. So this is what Breiman mentions in his paper, is that the data modeling culture focuses really on these regression models. So we have like linear, logistic, and COTS are some of the famous ones, but there are many other ones. But the idea being is that there's it's like you're approximating nature with these specific models. So that's the data modeling culture. The algorithmic culture is basically saying that I'm not even gonna pretend to know like how or model how complex nature is. I just know it's complex. And so I'm going to treat that as unknown and use some sort of algorithmic approach to come up with some sort of prediction. So I'm almost like bypass really understanding what is the relationship. So the numerical relationship between X and Y. And I'm just going to focus on getting the best combination of my X's to be able to predict Y. Again, and so again, unfortunately, or as Breiman predicted, statistics has focused a lot on this, what's written here as inference. So the way statisticians usually see the world is in terms of the statistical inference, and this was led by Fisher in the 1920s. Okay, whereas if you kind of flip the script and you think about machine learners, it's kind of the opposite in terms of like how they see the world. Okay, and there's no, it's hard to debate now, especially with the advent of deep learning and artificial intelligence, and how often you see it, not only just in the media. This is not just fluff. Like there's definitely something here, and they're doing important work. There's a lot of theoretical computational contributions as well, and part of that reason is that they focused on this prediction task. Almost, as Breiman stated, it's a lot more difficult to do the inferential task because you're asking basically for us to try to figure out what nature's doing. And at the biological level, it can be a very complex model to try to actually describe. So yeah, this is kind of how we represent data in terms of matrices, and really what I wanted to show here is that the focus is different. So when I talk about when I'm talking about prediction, really what we're talking about prediction is on the n level. So here n are the number of observations and p are the number of variables. So the prediction really is focusing on the n part of this data set. Okay, whereas the explanation is really focusing on the columns of my, what we call our design matrix or our predictor matrix. Okay, so it's really, the focus is different, but sometimes they're kind of used interchangeably, unfortunately. And what I'm going to try to show, or at least show through numerical examples, is that really, trying to be somewhere in between is probably not the best idea. As much as we want, often the answer I get is, yes, I want good prediction, but I also want to be able to interpret my results. Okay, and what I'll try to justify or try to explain, or at least get you to think about, is that maybe this is not the best idea. And if we think back to that quadrant, those 4 quadrants that are showing, maybe you want to be in those, the top left or bottom right quadrant, but not somewhere in the middle. Is that really, if you're focusing on explaining, then focus on that. Don't focus too much on the prediction aspect. So yeah, so in the next couple of slides, I'll kind of show the two different approaches. So the data modeling approach, again through a real data example, and then the prediction modeling approach, and some of the drawbacks of kind of both approaches. So this idea, so a lot of this information and a lot of these ideas come from this recent paper by a famous statistician, Bradley Efron. And so if you're really interested, I recommend reading this article, and this is kind of my interpretation of it. Okay, so this is what I would call a traditional regression model, and in this paper, Bradley Efron calls it a surface plus noise model. Okay, and so what does he actually mean by that? So this relationship here, this y equals what we call a linear predictor sometimes, or a surface, is just basically showing we're trying to really describe nature. So in that picture of X going through some sort of box and then going to Y, this is one of those options, and that's linear regression. Okay, and so this is how we would write this regression model, and we always assume that there's, the observed data is measured with some sort of noise. Okay, and so this is kind of what we call the deterministic part, or nature. Like, this is how we think nature is operating. And then, we have this noise because, of course, we don't get, again, this comes more to like the fact that, we don't have infinite amount of data. And usually what this means is that, our response variable is measured with noise. So one example that he gives in the paper is this, so I'll focus first on this left-hand side, is this relationship. So Newton's law, this F equals ma, this famous law that Newton came up with. And so this is what Newton or what Bradley Efron would call the surface part of the model. So this being that, there's a perfect relationship between force, mass, and acceleration. Okay, so that's why you have this smooth surface, and this can be seen as the x beta part of the model. Unfortunately, data is not this clean. We don't observe anything so smooth in practice in observational data, and what actually we observe is something here. So this part here is kind of the surface plus the noise. So again, a lot of statistics, especially the regression aspect of it, has been focused on basically going from here, right? So we have our surface plus the noise. So it's very jaggedy, lots of noise going on. We don't see a clear relationship, and kind of extracting the surface from this noise. So basically what he was trying to argue is that if Newton collected data, he did collect data, he would have gotten something like this. He wouldn't have gotten this clean relationship. It would have taken lots of experiments to get to the point where he figured out this very famous law. But again, my point here is that this idea of going to the surface plus noise model and figuring out what the surface is, that's another way of seeing what we're trying to do in these explanatory or regression based models. So going back to that CVD risk example, so this is another maybe hint, or maybe something that might influence your decision on seeing where that CVD risk calculator goes in that graph that I showed. And so in that paper, so I looked a little bit into the paper, and so I have a bit of an idea of what they did. And so they present this table too. So this is a regression coefficients and hazard ratios. Okay, and so we can let the stargazing begin, and we see right away that surprising or not, depending on how long you've been in this field, this was surprising to me to see that every single coefficient is kind of super significant. Okay, and we can almost ignore the p-value column and even look at the confidence intervals, and they look pretty strong, pretty convincing evidence that all of these predictor variables are quite associated with time to CVD. Okay, and so right away you kind of get a sense that they built this so-called prediction model, right? So if you look back at the calculator, you didn't see these coefficients, you just saw the inputs, and then you saw an output. You saw the risk, which is a prediction. But that prediction model turns out was actually based on these specific regression coefficients, which they actually did some sort of selection behind the scenes. Okay, and so what I'm trying to say is that in the end, what they ended up with is this kind of formula for the 10-year risk. Okay, and so you can kind of ignore this part here that doesn't really matter. What I want you to focus on is really this piece here. Okay, so this is the X beta that I mentioned before. So that's our linear predictor. That's kind of the meat of what's driving the prediction. The rest is kind of just details about how you get these specific probabilities. But if we just focus on this X beta part, or that surface part, this is what they came up with. Okay, so based on these this fitted Cox model, they ended up with this formula for calculating the 10-year risk. Okay, and so there's a few peculiar things. As I mentioned, I find it quite odd that everything was super significant. And when you look back a little bit at their methodology, you see that they actually removed, predictor variables that were not significant from the model. Okay, so this kind of two-step procedure. Okay, and what that hints at is that they're under this understanding or belief that the models which contain the most significant predictors are also the models that will do the best prediction. Okay, and this is actually a very false pretense, right? And I can try to justify a little bit why, and maybe I can convince you. And so the idea is that these measures of statistical significance are, first of all, arbitrary. So you're coming up with some sort of arbitrary threshold to say that anything less than 0.05 is statistically significant. But when you're testing that significance, you're not testing for predictive accuracy. You're not testing, how well does this do when I keep this in the model in terms of prediction versus if I don't put it in the model. Okay, you're testing some sort of null hypothesis, which has nothing to do with prediction to begin with. So already it's kind of suspect to think that a model with the most predictive variables would also give you the best prediction. And maybe in this case, it didn't make that much big of a difference. But I still found it quite suspect that these p-values are so small. Other things that probably should go into consideration when you're developing these variables or these models is what is readily measurable, right? So maybe there are variables that are not shown here, and maybe they didn't include because it's hard to obtain those measurements in the clinic or in practice, right? And so that's something more that kind of goes beyond the discussion for today, but also something to think about of maybe why they chose these select few predictors. So that was for the kind of the data modeling culture. Now I'll get to more the prediction models. So for the prediction models, I'll focus on a very popular one. Even in medicine, we see random forests a lot, and Leo Breiman, who I mentioned earlier, is the inventor of this random forest approach. Okay, and the details here are not so important. There's a few things I do want to emphasize though in terms of random forests and how they differ really from that surface plus noise model that I was showing earlier, that X beta plus epsilon plus the noise. So perhaps the first thing that might stand out to you is that I'm not showing any equations here. Okay, and there's a very specific reason for that, is that there are no equations for a random forest. A random forest is what we would call a pure prediction algorithm. Okay, and so it's really based on an algorithm. Really, it's you can't show any sort of formula. So when you're describing random forests, you either see pictures like this, or you see some sort of step-by-step approach of how to go about running a random forest model. Whereas when I introduced linear regression, I went straight to an equation, because you could very clearly see that's how it's defined, and you can see how I'm trying to model the surface or how I'm trying to model nature. And here I'm kind of bypassing all that and saying I'm going to go through an algorithmic approach. And so the way, just maybe very briefly how random forests work is that you start with kind of your data set and you create these what we call bootstrap samples. So bootstrap samples are just kind of sampling your rows in your data set with replacement. Okay, and you can do this many, many times. And for each subsample, you build this kind of tree, this kind of what we would call a classification and regression tree or a decision tree. Okay, and so each tree will be a little bit different because it's based on a different data set essentially from your original one. And then once you've come up with the whole tree, you come up with a tree for each of the different bootstrap samples, then you'll come up with a classification or a prediction for each of the different trees. So tree in this example, tree 1 says class A, tree 2 says class B, and so on and so forth. And then you end up with this kind of majority voting. So you take the class which was voted the most, and that's how you predict whether or not this patient goes into class A or class B. Okay, and so again, a lot of details are definitely skipped over here. I can definitely suggest references for random forest, but this is a quite popular technique, and the emphasis here is really on the fact that there's no formula. Okay, and so this is how it would be presented in a stats textbook. As you can clearly see, there's no sort of formula. What you have are basically steps that you have to go through to come up with a random forest model and random forest predictions. And this is in stark contrast to that linear regression model I showed earlier, or even that CVD Cox model that I showed earlier. It's very explicit. You can see exactly what's going on. There's no ambiguity. So again, in this paper, I'm taking an example from the paper. What he did was he used this microarray study of prostate cancer. Okay, and so in this specific example, what they're doing is measuring the gene expression levels on 6,000 genes in 102 patients, 52 who have cancer and 50 who don't. And again, the idea here is, are there specific genes that might be enriched in cancer patients versus controls? Okay, so in this specific example, we have 52 cancer patients and 50 controls, and we have their gene expression measurements on 6,000 genes. And this, what I've shown here is just a data matrix. Again, the previous one I showed was kind of long, and this one's kind of wide, kind of indicating that this is suitable for kind of this is not suitable really for a traditional linear model, because we're what we call in the high dimensional setting, where the number of variables are much larger than the number of predictor variables. Okay, and so in this specific example, what he did was he randomly, and this is important, he randomly divided the data set into training and test sets. Okay, so a training set is where you would train your model, and a test set is where you would test the prediction performance. Okay, and this is something machine learners do very well. They've thought a lot about this. Statisticians have also thought about this in the form of cross-validation. But the idea is to basically say that, I don't want to overfit on if I just use the whole data set. I want to get an unbiased view of what the actual error rate might be. And so what I'll do is I'll split my data set into two pieces. So I'll train on one piece and then test on another. And that gives me kind of a better or more accurate view of the out of sample performance. And this is one of the key features of machine learning. In fact, like this is how they test, how good their algorithm is really this out of sample performance. And whereas in the surface plus noise world, or in the regression world, and the stargazing world, it's all about your in sample performance, right? So you're looking at those statistical significance measures, those confidence intervals, all of that is kind of within sample. And so just to give you again maybe a clearer picture of what's actually happening for those who might not be familiar with this procedure, this is a kind of a complete sample of 26 patients, which I've labeled from A to Z. And so what you would do is split your data. In this example, I didn't do it randomly, but you could do it randomly. So I've just stopped after 25 or 20 letters. And so what I do is I train this kind of decision tree, a very simple one where I only have one predictor, and I basically all I have to do is answer the question, are the years of in this example, it's I think years of service, and if your years of service is less than 4.5, then you get predicted a value of 226. If it's greater than 4.5, then you get predicted a value of 697. Okay, and so how this works is that I get this model just from the training set. So I didn't use this test set, those other 6 observations, and so I use for each of my test sets, I have the value of their years, so that's a covariate. I have their observed value, so these are their observed values, and then I can fill in the predicted values based on my training model. So again, like I said, for those who have years greater than 4.5, they get predicted a value of 697, because that's what the tree is telling me to do. And then everybody with less than 4.5, they get predicted a value of 226. So now I have this kind of predicted value on my test set, and that's kind of an unbiased view of my error. And then I can calculate some sort of measure of fit or measure of accuracy. So in this case, because it's a continuous y, I can do something like a mean squared error, where I'm doing the observed in the test set minus the predicted in the test set. Okay, so this is kind of what I mean when we do data splitting or out of sample predictions. This is kind of fundamentally what's happening. Okay, and so there's many variations on this, but one of the key points is that this is kind of what happens. And this can be generalized. So that was kind of one random split, and we can kind of do this again and again for kind of different splits. So in this example, this is what we call 5-fold cross-validation. So you'll see that I train my model. So everything that's in blue is what I use to train, and everything that's in beige is everything that I use to test. And so in 5-fold cross-validation, we fit the model 5 times, and we get 5 kind of test errors, and we kind of average them. And so this is a typical machine learning approach, and some models and statistics use this approach as well. And this is exactly kind of what random forests are doing. So again, I just want to show now what the error rate looks like. So here again, this is the error rate on the test set. So that test set that I left out, that wasn't included in my training, this is the error rate. And the x-axis here are the number of trees. So the number of trees here are just the number of bootstrap samples. And so what we can see here, or what I want you to focus on, is that once we get to about 100 trees, the error rate, the test set error rate, so this is kind of a unbiased view, gets down to 2%. Okay, so basically we're making, out of every 100 patients, we're making 2 errors, which is quite remarkable, right? So we have, again, we have this very tiny sample size, 100 patients, 6,000 genes, and we're somehow able to get a 2% error rate, which is quite good, I would say. So because we're using 100 trees, this becomes a very complicated model, and one thing people ask for a lot is what is actually driving these predictions. And so in random forest, you don't get this p-value, you don't get a confidence interval, you don't get an effect size. What people have thought of is getting some sort of measure of variable importance, right? And so however that's calculated is not really important. What you kind of see this as is kind of, again, just a measure of importance. How important in this example are the genes in my prediction? And so what's being plotted here are the variable important measures for 348 genes. And the reason why there's 348, because that's what the random forest used. It never actually needed to use any of the other, 5,500 genes. It just used these 348 ones. And these happen to be the ones that had an importance score greater than 0. So you can see there's a few here at the top that are super important, and then slowly kind of decays down all the way to 0. Okay, but the point is that to get that 2% error rate in the test set, basically the random forest used a lot of trees and it used 348 genes out of those 6,000. And so this is nice. We have this really good prediction. We have this really good prediction error on our test set. We have a handful of much smaller, right? 348 out of 6,000, much smaller set to maybe go to the biologist and say, my random forest used these 348. Maybe you can look into these instead of all those other 5,000 genes. Okay, and maybe the story ends here. There's kind of a limitation and a problem that's going on here, and again, that goes back to the idea of randomly splitting my training and test set. Okay, and so as you saw, I had those super important variables, and so what they did in this paper is they actually removed all 348 of them and then refit a random forest model. So that's this guy here. So in this final model, these are all separate models. In this last model that I'm highlighting here, they removed all those 348 important genes. So, if we were to go back to that CVD calculator, all the stargazers, so all those starred, those super low p-values, if we remove all of them, you're still getting so if we remove all of them, you're still getting, in this example, 0 errors on the test set. So in other words, the random forest is finding other variables to make important. Okay, and this is not an overfitting issue because I'm using an independent test set. And so this kind of gets to the idea that perhaps on its own, each gene is probably not very predictive of prostate cancer, or sorry, of the response here, which is prostate cancer, right? So, but a whole bunch of weak learners, so a whole bunch of small trees or small trees in the random forest can be combined to come up with a very powerful predictor, a very powerful prediction. But the message here that I'm trying to get across is that statistical significance or variable importance has very little, or sometimes can have very little to do with predictive accuracy. And really, these are two different goals that we should really have clear in our minds from the start when we're doing our data analyses. So there's a question about variable importance here.
Yeah, I don't have as much experience with random forest, but we did use it on one of our data sets and sort of compared its output to logistic regression. And really what comes out in the random forest that we used at least was that any variable that we tried not to change anything by transforming the variables. Maybe that's a mistake, but I think we didn't want to transform anything initially. And most continuous variables provided, like for example, age provides much more importance when you use like the feature importance than a binary variable, which makes sense. But, I don't know if it's because of just like a statistical issue or if it's really, that's what it means,
Yeah, I'm actually, I'm not super familiar with that issue. I guess, yeah, I think we have the same intuition that perhaps the continuous variables are kind of giving more information onto how to actually make the split. Whereas in binary, you can only go one of two ways. So perhaps that might be an issue. But in this specific example, they're all continuous variables.
Mm-hmm. Yeah, because I think like as a clinician, that like whether you're 50 or 51, like it's not a huge difference, but whether you're 50 or 75 makes a big difference. So, should we, when we're using random forest, try and kind of provide more information that clinically is classifying patients and not kind of continuous ones where there's so much spread? I'm not sure what the right thing to do is.
Yeah, I think yeah, it's a little bit maybe tangential to this discussion. I think, but mainly I think it's the idea is you want to try to give as much information as possible. And again, I think what it's kind of I mean, yeah, sorry, maybe it's not tangential. I think what you're trying to get at is kind of the interpretation aspect. So
Yeah.
like, the 51 versus 75 versus, 51 versus 52. Again, that's like more interpretation. But what I would suggest, or what we try to suggest usually is to try to give the model as much information as possible and not come up with these arbitrary dichotomizations that might be clinically relevant, but for the prediction, you kind of want the model to let it do what it's doing and not worry so much about the interpretation aspect.
Yeah. Thanks.
Thank you for the question. Yeah. So that was again, this point here, this table here is just showing that again, if you remove the most significant or the most important variables, it still doesn't make a difference in the prediction. Another thing that another thing that I wanted to point out is that this idea of randomly splitting the training and test set is something that is often done, but this can also cause some problems and actually mask some potential issues. Okay, so they kind of in this paper they redid this experiment, but instead of randomly dividing between train and test, what they did is they took the training to be the early, so the first ID numbers, so the first set. This is my train. And then the late ID numbers they used as the test set. Okay, and in this experiment, it just so happens that kind of the ID number 1 was basically the first patient in the study, right? And they were collected in this order, right? And so when they divided the training and test set this way, so in other words, it's not random anymore, it's really by how they entered the study or the order in which they entered the study, then they got something, drastically different. Okay, they got an error rate of 24%. So we went from 2% when we're doing a random split to 24% when we're doing the split by some sort of, ID number, where ID is a proxy for the time that you entered into the study. Okay, and so I think a lot of people in this room, a lot of the epi people, even the biostats people in this department would people at the core would be able to figure out what's actually happening, I think, right? So there's definitely some sort of bias that's happening. And if you're into microarray experiments, perhaps there's something different, right? So there's an unmeasured confounder here that's making it so that the training set is actually much different than the test set. So in other words, you can imagine a situation where, they might have used the Affymetrix. It's just a different array, version 1, and these guys use version 2. So this is how you measure the expression levels. And this was just a function of time, right? And this is something that's unmeasured, but very clearly what happens is that now these gene expression measurements in the training set, or these patients in the training set, are completely different with respect to the gene expression measurements than the test set. Whereas if you did it randomly, if you did that random split, they're comparable because you're kind of mixing, Affymetrix V1 with V2. And so that's why you were getting such good test set performance when you're doing this random split. And so this is, kind of one of the warning signs of this, train test split paradigm that sometimes can get lost in the machine learning world when you're not thinking too much about the data collected. And so I think, those of us who, many of us in this room, all of us in this room who have this kind of training with appreciating data, understanding data, the biases that can occur, it can be very useful in these prediction models, right? And so I know a lot of you, many of you, all of you will dissect the results and really try to hammer down on what's actually happening. And so this is one other kind of red flag I wanted to point out that can arise when you're using these machine learning models. And this is not this is kind of not this idea is sometimes called concept drift or data set drift. And a very famous example are these Google flu trends. So basically Google published in 2009, I think, in Nature, they published basically an algorithm for predicting influenza outbreaks. Okay, and the way they used, basically what they did is they used counts of internet search terms, and basically they kind of showed that they were outperforming the CDC, right? And so a few years later, what you're seeing, so at the beginning, you're kind of seeing all these lines overlap. So basically Google Flu is basically doing just as well as the CDC. And then after it starts this, you kind of see this orange line here. And what's happening is that Google is always predicting that there's an epidemic or that there's some sort of flu epidemic. Okay, and this is again the idea of concept of data set drift. In other words, they didn't update the models, a few years later, and this is kind of similar to what I was just saying about the prostate cancer example, is that a lot of these prediction tools are what we might call kind of short-term or ephemeral tools where it's good for a short period of time, but then there's so much that changes, whether it's in the way the data was collected, whether it's in the technology, whether it's in a lot of things in this flu example that that can affect the prevalence of the flu, that require the model to be updated. Okay, and so that's another kind of cautionary tale about these prediction models, is that usually when we think about them, they're kind of short term, or they should be used in the short term and then constantly updated. This is not something that you can just develop once and hope and expect it to work 5 years down the line, even a year down the line. And this is one famous example. One thing that often gets asked is that this is machine learning, it's all black box, and I don't really understand what's going on. That's a massive criticism that I hear a lot, right? And it's almost like we need to understand what's actually happening. And so one example that can be used is the example of deep neural networks. Okay, so deep neural networks is just some sort of model that can detect objects, and so here this is one example where they have this chest X-ray, okay, and they're trying to use deep neural networks to detect for positive pneumonia. And so I'm not a radiologist or a doctor, but basically these networks are notoriously known to be not interpretable. We have no idea what's actually going on, and so lately there's been kind of some development in terms of trying to understand what is actually being used for the prediction. Okay, and so the way they do that is that they come up with these so-called heat maps or saliency maps, where the darker the color, so the red in this example shows that this piece is being used. Okay, and so if you're a physician or radiologist, you might look at this and say, oh yeah, this kind of makes sense that this red area, it makes sense. If I was looking at a scan myself, I would probably look at that area too and diagnose pneumonia that way. The problem with this approach is that it's non-scientific. There's no objective measure that you're using. It's purely heuristic and based on what limited to what and again, there's no objective measure. We're not talking about prediction accuracy on an independent test set. We're not talking about validation accuracy or anything like that. It's purely heuristic, and that's one of the issues with searching for interpretability, is that's kind of the cost, and that's actually nature. Nature is so complex, biology is so complex that maybe we shouldn't, the gold standard should not be a model that's super good at predicting, but also that we can explain what's happening. Models like this should be, of course, validated again and again and again and tested, of course, but to ask a model to be both interpretable and super good at predicting, that's a little bit of a stretch. Okay, and another example, maybe in the interest of time, I'll skip this, but another example is Tylenol. So Tylenol we've been using for in this like 100 years, and we don't, at least until 2005, we didn't really understand the biological process. Like, why is it actually working? We know from RCTs that it works and it's not harmful and so on and so forth, but the biological process is so complex that we don't actually understand what's actually happening. And this was actually a little bit of a shock to me, but this is one of the famous examples used where the prediction's really good. We feel less pain when we take Tylenol, but not understanding the process, it's okay. We know that it's working. And again, this is, I don't want to paint the picture that there's only one right way. I'm sure there's many people who can debate a lot of what I'm saying, but this is just one point of view, and my goal here is to raise some discussion as well. So just as a comparison, I just want to again highlight maybe some of the things that I mentioned in the traditional regression methods versus the pure prediction algorithms. So the traditional ones again are surface plus noise, whereas the pure prediction ones, again, like it's very discrete, so we don't have these smooth surfaces that you end up with. Another thing, again, to highlight in some of the examples that I just mentioned, again, regression methods are after the eternal. Like, what is the actual biological truth here that I hope will last forever? That whether it's year 1, year 2, year 3, I know smoking causes lung cancer type of thing. So that's for the eternal. Whereas prediction accuracy is possibly short term. And yeah, the rest I'll leave for later, just in the interest of time. And I just want to end with some take-home messages from this presentation. Explanatory power is not equal to predictive power. So just because you have a model that's really good at explaining does not automatically imply that it's going to be really good at making predictions. Okay, and so this idea of filtering on most predictive or most significant variables is not the best idea. And again, the best explanatory model is not necessarily the best predictive model. I just showed one counterexample of that, where we removed 350 of those most important ones, and still the prediction was just as good. Message 2 is the explanation versus prediction. So again, explanation is all about in sample, prediction is about out of sample. And really, in sample is all about the interpretation, significance, goodness of fit, whereas out of sample is about prediction accuracy, right? And again, it's about the type 1, type 2 errors versus overfitting. Like, that's what the main concern is in the prediction world. And the third message here is that explaining is harder than predicting. So the eternal versus ephemeral, right? And so finally, I just want to end on my last question. I hope we can, sorry for going a little bit over time, but if someone has their thoughts on what they think now, please let me know, where you think that CVD risk calculator lands on this quadrant. I really thank you for your time. Thank you for taking an hour of your day to listen to me talk.
Thank you very much, Sahir. That was a really nice presentation, and I see some questions in the chat. Maybe you can answer the one from Kaveri. She asked, does a machine learning ever involve computational scientists integrating possible functions or equations?
So yeah, so I mean, I take that to mean maybe perhaps like kind of domain knowledge or kind of external knowledge or some sort of prior knowledge, perhaps. I think the good ones do, definitely, the ones where you have the collaborations, the ones that this has been my experience, kind of in radiology, is that the machine learners kind of come to us for the data sets, and kind of vice versa. We kind of, or the radiologists give them their input into kind of what should be used, right? And so that's just one example when we're trying to analyze images. But yes, I mean, even in this microarray example, there's ways of incorporating prior information, like, for example, like in specifically the microarray example, we know that certain genes, encode for certain proteins, and this is based on external information, right? And so it wouldn't, and so this would be maybe one way to prioritize your model or your strategy, right? And it can be shown, and people have shown that perhaps too much noise is a bad thing, right? And so even in these machine learning models, if you have too much noise, meaning you don't have enough observations, this can diminish the performance of those models. So yeah, definitely. I mean, I'm always for interdisciplinary research. If you look at maybe my website or just even my biography, that's something I try to emphasize. And it's no different here. I think a lot of these machine learning models can benefit from domain knowledge, and I think that's that's going to be super important, particularly when my experience is biased towards the health science, right? So I'm not talking about, Netflix and Google and those guys. They're definitely doing a good job. They figured a lot of things out, but the skepticism that I mentioned in my abstract, I think is still very relevant in the health sciences because of the small samples we have, because of the biases. I don't think any of that training is for naught. Like the epi training, I think is super important in terms of appreciating or respecting the biases that can occur in observational data.
Thank you very much, Sahir. I'd like to kind of officially thank you so that people get a chance to say that as well. But can you just stay on a few more minutes?
Of
There's
course,
a few questions.
Yeah, I'd be happy.
There's a question from Guang Shang. Guang, do you want to speak up and read out your question? Okay, I will then. Well, yes, yeah, please do.
Hi, thank you, sir, so much for the clear presentation. Just wonder, when you use the random forest model, do you use the mean decreased accuracy or mean decreased Gini parameters to choose the variables in the clinical trial?
Yeah, in clinical trials, I mean, I don't have much experience there. I think it depends again on, I think they're kind of after two different things. I mean, again, I think the accuracy is more about prediction, whereas the GNI score is more about which variables are important in those splitting rules. So again, I think it really depends on the context and what you're trying to do. I mean, even within the random forest model, I realize there's different accuracy measures, but they should be taken, I think, with a grain of salt. I mean, I think maybe a bigger question is do you need to choose variables to begin with? I think could be one of those things and one of the main points of my talk.
Okay.
Yeah, thank you so much.
Thank you. And a question from Cindy.
Yes, hello. I had a question about your example about when you showed that not randomizing observations for the training and testing split kind of decrease the predictive ability of the model. I was wondering if you would expect different results if we incorporated information on when the data was collected.
Yeah, that's a great point. So again, we're well versed in this idea of unmeasured confounding and how that can affect results. So definitely, I think again, that was a hypothesis that the expression measurements were on different chips, but we could definitely see a world where we actually have that information, and we would expect definitely if we included that information that could definitely impact the prediction. The problem there becomes, and Cindy, I'm sure you know this, is that when we're thinking about prediction models, we have to think about what's coming next, right? Are these variables going to be measured going forward? And more likely than not, that chip type is probably not going to be available a year from now. And so, if you include that variable in your prediction model, then is it really a prediction model? And how do you actually kind of use this to go forward? And so that becomes an issue as well.
Thank you.
Yes,
Thank you for the questions and for the answer. I have a couple of questions, if you indulge me.
Sure.
I want to ask, you mentioned at some point N is more important for prediction models and P for explanatory models. I mean, I don't know whether important is the correct word, but
focus. Yeah, I would say the focus is on the N. Like, it's just a crude way of, I guess, of seeing things, is that the focus in explaining is really like if we look at just that prediction matrix. What I was just trying to say is that the N part of this design matrix is really what the prediction is about, whereas the P part of the matrix is really about the inference. But yeah, of course, they're both used. I mean, this whole matrix is used in both approaches.
I mean, though it's like, I suppose a good prediction model does need a lot of P to be high.
I mean, yeah, I mean, I mean, it's hard to come up maybe perhaps with a hard and fast rule, but definitely it seems that a lot, like I think the idea, especially behind random forest, is that a lot of weak predictors, many of which, especially in microarray experiments, are highly correlated, can amount to better prediction than, you know, picking the first principal component or just, you know, getting rid of everything that's correlated with like the most expressed gene or something.
Okay, all right. Yeah, and explanatory variables often come with rules like, you know, the thumb rule that people often learn for logistic regression. You must have so many outcomes per predictor, whether or not that's accurate. I mean, still, we're kind of conscious that you can't stuff too many predictor variables into a model. So it's almost like we're saying we can't, you know, we're acknowledging we cannot do very well.
For explanatory, I think for explanatory, definitely there are some limitations as to what can actually be done, and these rules of thumb, you know, definitely have some scientific basis. I think I've seen quite a bit of you know, simulation studies on that aspect, but I think again the focus is on, you know, the causal models, the inferential models. When it gets to prediction, I'm not so sure. Yeah, I'm not so sure. I'm not as convinced that would have a negative impact.
I'm going to go back and read that literature again now. I have my second question is this. You know, recently I had the experience of fitting a cart model. So not a forest, but just a single tree.
Sure.
And that model picked variables that were completely different from what you would get from a logistic regression model with a, you know, linear predictor. And why is that? Is it what you're saying that cart model is picking up combinations of variables? You know, maybe the individual predictor is not focusing so much on the individual predictors, but on the combined information across them.
Yeah, I think there's a few reasons. I mean, specifically to CART, I think the way it works is that it's a greedy approach. It's a greedy algorithm in the sense that the first split is almost randomly determined. So you know, it could very well be that if you rerun CART again, you'll get a different kind of first split, and because it's an NP-hard problem to try to go through all possible splits.
Right.
And so I think that's part of the reason for the poor, you know, potentially poor predictive accuracy. And one of the motivations for random forest is that because of this randomness or greedy approach that we should use, combining many trees. And then again, I think the other thing is that, you know, the logistic model is in essence a linear model, and so I think the relationships are different, and so whether or not you get the same result, perhaps, you know, I think it could be debated that, you know, they don't have to necessarily be the same.
Well, thank you very much. That was very illuminating. Anybody else with questions? I'm not seeing any other questions. I think a number of people commented that it was a very clear talk and used a plain language approach. Sahir, that was appreciated. So thank you very much.
Thank you so much. Thanks for taking the time and for the invitation.